So let us start the discussion on the deflections of prestressed concrete beams. So actually there are two types of deflection that is or that are being experienced by a prestressed concrete beam. So the first type is the instantaneous or initial or short-term deflection. So these are the deflection or deflections that are being experienced by the prestressed concrete beam as it supports the loads that are supposed to be carried by it in the short term with respect to short term period, meaning these deflections that we will see here occur on the prestressed concrete beam uh, immediately after the application of the load. So these are actually not time dependent deflections, which is actually the time-dependent deflections is actually the second category of deflections that we will study on this discussion, which are the long-term deflections, which are actually time-dependent deflections that actually occur on the prestressed concrete beam after some time. So this first type of deflection that we are studying here are the deflections that are being experienced by the concrete beam or concrete element uh, immediately as it supports the loads that are supposed to be carried by it. So again, these deflections that we're talking about occurs immediately upon the application of a load, just like what I have said a while ago, uh, which are caused by elastic deformation of the concrete in response to the loading. So the effect of creep and shrinkage are not considered here, obviously, because the effect of creep and shrinkage are actually time-dependent effects, which will fall under the second category of deflection, which are the long-term deflections. So the deflections that are dependent on time, the deflections that change its magnitude with respect to time. So for this part of the deflection topic that we are studying, we will just focus on short-term deflections, which are again deflections that occur immediately after the application of load that are to be carried by the prestressed concrete beam that we are designing. So the first short-term deflection that we will study on this discussion is the total camber that is being experienced by the prestressed concrete element that we are designing. So actually the total camber that is being experienced by the prestressed concrete beam that we are designing is actually due to the effect of the prestressing force and the weight of the concrete element itself. Therefore, the formula for the total camber that is being experienced by a prestressed concrete beam is equal to this formula, wherein the positive or negative sign indicates that the deflection is actually going up, and the positive sign indicates that the deflection is actually going down, or it deflects downward. So that is the meaning of the signs that you are seeing here. So again, using this formula, you can see that the total camber that is being experienced by the prestressed concrete beam is actually the sum of the deflection due to the initial prestressing force alone and the deflection due to the self-weight of the member alone. So if you can remember from our previous discussion, we have seen that whenever the prestressing force is already transferred to the concrete element that we are designing, the concrete element tends to bend upward, thereby making it experience what we call camber, which is equal to this, which is actually an upward deflection. So that's why we put a negative sign here. So that deflection, that upward deflection due to the initial prestressing force uh, is equal to this term here. So again, after that, after the beam already bended upward, it will be like a simply supported beam, thereby making it support its own weight. And that as as it supports its own weight, it also experiences deflection, which is actually a downward deflection, which is actually the term here. So again, that is a downward deflection. That's why we indicated a positive sign. So those two deflections actually act on the prestressed concrete beam initially. So if you will try to compute the total camber that will be experienced by the prestressed concrete beam, it is actually the sum of the deflection due to the prestressing force alone and due to the deflection uh, of the beam due to the self weight due to the scenario of supporting its own weight. So that is that is how you can compute the total camber that is being experienced by the concrete element. So the total camber is not only dependent on the deflection due to the prestressing force alone, but it also depends on the effect of the deflection due to the self weight of the member as the member supports its own weight. Because again, we can imagine that as the beam deflects upward, the self weight of the beam will tend to bend the beam downward with a magnitude equal to this. So therefore, if you will try to find the total camber that was experienced by the prestressed concrete beam, you just have to add the effect of the deflection due to the prestressing force alone and the deflection due to the self-weight of the member. So that is how you can compute the total camber that is being experienced by the prestressed concrete beam. So that is actually a short-term deflection because it immediately occurs on the prestressed concrete beam as the prestressing force is applied to the concrete beam itself. So that falls on the short-term deflection category. And then, if we have short-term deflection, we also have obviously a long-term or final deflection. So this deflection is actually the deflection under permanent loads and superimposed service loads in consideration to effects of usage and time, which is the final stage of the deflection that is being experienced by the prestressed concrete beam. So this deflection that you are seeing here, the long-term or final deflection, takes into account the long-term shrinkage and creep movements, which are time-dependent deflections. So as we have studied from the previous meetings, uh, as shrinkage and creep occurs on the concrete, there will be a deflection that will be experienced by the concrete element that we are designing, especially if the loads are sustained loads, meaning the loads are applied to the concrete element at a very long time. So this affects the deflection due to shrinkage and creep just occurs after a certain magnitude of time. So they not occur immediately after the imposition of the loads, but they just occur after a certain magnitude of time, unlike the short-term deflection, wherein the deflection already occurs as the loads are applied to the concrete element itself. So the formula for the final deflection, if you want to find the final deflection, you can use this formula here. So what are the things that we are seeing here? So this first expression here is actually the short-term deflection due to the permanent loads. So you can see here the short-term deflection or the total short-term deflection is just the sum of the deflection due to the pre-stressing force alone, due to the self-weight of the member, due to the superimposed dead load applied to the member, and due to the sustained live load being supported by the concrete element. So take note that the pre-stressing force that we are considering here at this stage at the final deflection, at the computation of the final deflection, is already the effective pre-stressing force, because again we know that at this particular stage, actually this is actually the part of the service load condition wherein the concrete beam already supports the remaining service loads that are supposed to be carried by it. So you can expect that the pre-stressing force already acting at the concrete element at this particular stage is already the effective pre-stressing force, meaning the pre-stress loss or pre-stress losses already occurred on the pre-stressing reinforcement. So that remaining force on the pre-stressing force, I mean that remaining force at the pre-stressing reinforcement will again also induce deflection, which is actually an upward deflection. That's why we have put a negative sign here to indicate that it is an upward deflection. That effective pre-stress force, that remaining pre-stress force acting on the pre-stressing reinforcement at this particular stage, will still induce an upward deflection that will be counteracted by the deflection due to the self-weight, due to the superimposed dead loads and sustained live loads. And again, those effect that deflection that you can compute here is actually short-term deflection. So that deflection actually occurs uh, immediately after the application of the load. So actually, this is part of the short-term deflection, which actually plays a role on the computation of the final deflection. So because the final deflection is a function of the short-term deflection plus the long-term effects of the shrinkage and creep. So this is the part wherein we take into account the long-term effect or long-term effects of shrinkage and creep with respect to deflection. So these are actually the long-term reflection of the permanent loads, wherein we already considered the creep effects. So we just multiplied this term with respect to we just multiplied this term with Cu, which is the creep coefficient. If you can remember the Cu that we have studied from the previous discussions. So that is how you can take into account the effects of the long-term effects of the shrinkage and creep with respect to the deflection. So the long-term effects is just a portion of the short-term deflection, as you can see here on the formula. So usually Cu is a fraction less than 1, meaning the long-term deflection or the long-term effects of shrinkage and creep with respect to deflection is just a portion of the short-term deflection that is being experienced by the concrete element. And in addition to that, if there will be an additional live load that will be applied to the concrete element, therefore, the total final deflection or long-term deflection will have will be considering also the effect of that additional live load. So you can see here that if there will be an additional live load, the effect of that additional live load, the deflection due to that additional live load, will play also a role on the computation of the total final deflection. So this is actually the short-term deflection of the total additional service loads. If there will be additional service loads, total live load service loads. So you just have to take note the formula for Cu. So Cu, the creep coefficient, is just the ultimate creep strain divided by the elastic strain. So I hope you can remember these terms that we are saying here. So the ultimate creep strain is the maximum magnitude of the strain that will be experienced by the concrete element due to creep. And then the elastic strain is actually the strain that will be experienced by the concrete element due to short-term effects, due to the effects of due to the immediate effects of the application of load. So that will be the elastic strain here. So this is actually a short-term effect, and this is actually a long-term effect. So that is the formula for finding the deflections that will act on a prestressed concrete beam. So for the computation of the specific magnitude of deflection, we can use these formulas uh, that we will enumerate here. So for the computation of the deflection due to the prestress force alone, say for example, if the tendon profile is straight like this, the deflection or the maximum deflection that will be experienced by a prestressed concrete beam with a straight tendon profile is equal to this. Actually, the maximum deflection that will be experienced by the prestressed concrete element with a straight tendon profile will occur at midspan. So that magnitude of deflection is just equal to this, the magnitude of the prestress force that will be transferred to the concrete element times the eccentricity at the center, which is in this case, since the profile is straight, the eccentricity at the center is actually the eccentricity all throughout the length of the beam. And then L is the span of the beam, the length of the beam. E is the modulus of elasticity of the beam, and I is the moment of inertia of the cross-section of the beam. So that is the formula for finding the deflection due to prestress force alone. Okay, you have to remember that the formula is the deflection due to prestress force alone. So considering only the deflection due to application of prestress force. So other formula is for a prestressed concrete beam with parabolic tendon profile like this, with an eccentricity at the ends equal to 0, meaning the tendon at the ends uh, uh, are located exactly at the location of the centroid or neutral axis. That's why there is no eccentricity at the ends of the prestressed concrete beam. So for finding the deflection that will be experienced by prestressed concrete beam with parabolic tendon profile, we can use this formula here. So the maximum deflection that will be experienced by a prestressed concrete beam with a parabolic tendon profile will occur obviously at midspan. And that the magnitude of that deflection at midspan is equal to this. 5 times the magnitude of the prestress force that will be transferred to the concrete element times the eccentricity at the center times the span of the beam itself divided by the product of 48 and the modulus of elasticity and the moment of inertia of the concrete section. So for the case of prestressed concrete beam with single bent up tendon profile like this, with an eccentricity at the ends also equal to 0. So the deflection acting at this particular beam, which actually occurs at the midspan of the beam, is equal to this formula. So the product of the prestress force to be transferred back to the concrete element times the eccentricity at the midspan section times the span of the beam divided by the product of 12 and the modulus of elasticity and the moment of inertia of the beam itself. So additional formulas for finding the deflection due to prestress force. Actually, these formulas now that I will enumerate here are general formulas. So actually, you can derive the formulas that we have shown a while ago using these formulas that I will be showing here. So say for example, for a prestressed concrete beam with parabolic tendon profile with an eccentricity at the ends not equal to 0, meaning the location of the tendon at the supports are not actually coinciding with the neutral axis of the uh, concrete beam. So there is an eccentricity at the ends, at the end supports as well as at the midspan. So the formula for the deflection that will be experienced by prestressed concrete beam with a parabolic tendon profile in general is equal to this formula. So again, the maximum deflection occurs at midspan or at the center. So that magnitude of deflection is equal to this formula here, the magnitude of the prestressing force times the span of the beam divided by the product of 8 EI, modulus of elasticity and moment of inertia, times the product of 5 over 6 and the eccentricity at the center, plus 1 over 6 times the eccentricity at the ends. So actually the formula that I have derived or I have shown a while ago for parabolic tendon profile with an eccentricity at the ends equal to 0, you can derive that formula using this formula. You just have to change EE here, the eccentricity at the ends, to be equal to 0. You just have to change this to 0 and then simplify the equation, and you can see that the formula that will come out is just the same as the formula that I have shown a while ago for the case of parabolic tendon profile with an eccentricity at the ends equal to 0. So you can try to check that. And then for the case of prestressed concrete beams with harp tendon profile such as this, with an eccentricity that at the ends not equal to 0, and with a bent up part, which is actually a double bent up tendon profile, because we have two parts here that are bent with a length of the pre-stressing reinforcement on this part of the concrete beam equal to A, and if the total length of the beam is L, and if the distance of this bent up here from the support is equal to A as well as on the other side, therefore we can see that the length of this part of the pre-stressing reinforcement is just equal to the total length minus the sum of these two, or in other words, L minus 2I. So the deflection that will be experienced by the prestressed concrete element for this particular case with a harp tendon profile due to prestress force alone, again, all of the four formulas that I am saying here are just due to prestress force alone. So the formula for the deflection acting on this particular prestressed concrete beam is equal to this. So again, the maximum deflection that we're talking about here occurs at the midspan or the center of the beam. So it is just equal to the product of the prestressing force and the span, the square of the span, over 8EI, modulus of elasticity and the moment of inertia, times the eccentricity at the center plus 4/3 of the ratio of the distance here divided by the total length of the beam, and then square it, and then multiply to the difference between the eccentricity at the ends and at the center. So again, you can derive actually the formula for the single bend up profile that I have shown a while ago. Just have to make EE here, the eccentricity at the ends, equal to 0, and then simplify the whole equation. So you can see there that the formula that will come out is just the same as the formula that I have shown a while ago for single bent up tendon profile. So those are the formulas for finding the deflections due to pre-stress force alone. So for the deflections due to gravity loads, which are the imposed loads, superimposed dead loads, live loads, as well as the self-weight itself, you can find the deflection due to those loads using these formulas. Actually, we have already uh, known these formulas for a long time, as we studied the course theory of structures, or as early as the subject mechanics of deformable bodies. So we are already familiar with the different deflections that will be experienced by a concrete beam with different load conditions. So say for example, if the beam a simply supported beam with a load equal to a uniformly distributed load with a magnitude W, according to this table, the magnitude of the deflection that will be experienced by this simply supported beam loaded by this uniformly distributed load W is equal to 5WL to the fourth over 384 EI. The product of 5 and the W, the magnitude of the uniformly distributed load, and the fourth power of the total length of the simply supported beam divided by 384 times modulus of elasticity of the beam and the moment of inertia of the beam. So usually the maximum deflection that occurs for this case uh, occur at the midspan. So usually the maximum deflection for a simply supported beam occurs at midspan. So you can expect here that the formula is the formula for the deflection at midspan. So that is only for the case of simply supported beam loaded with a uniformly distributed load. So for the case of a simply supported beam loaded by a concentrated load P at the center of the beam, the deflection at the midspan or center of the beam is equal to this PL cube over 48 EI. So the P here, again, I hope you will not be confused with the P that we are talking about here. The P that we have shown a while ago is the pre-stressing force. So now, for the case of gravity loads, for the computation of the deflection due to gravity loads, the P that we are talking about here is the magnitude of the concentrated load applied to the simply supported beam. So the deflection at midspan for a simply supported beam loaded by a concentrated load at midspan is equal to the product of the concentrated load and the cube of the length of the whole beam divided by 48 times modulus of elasticity of the beam and the moment of inertia of the beam itself. So for the deflections of other type of beams loaded with different load conditions, you can just refer on this table. And then additional formulas is shown here. So for the case of a beam fully restrained at both ends and supporting a uniformly distributed load W, the maximum deflection, which actually occurs again at midspan, is equal to this formula, WL to the fourth over 3 for AEI. The magnitude of the uniformly distributed load and the fourth power of the whole span divided by 384 times modulus of elasticity of the beam times the moment of inertia of the beam. So if the fully restrained beam supports a single concentrated load acting at midspan, the deflection at midspan is equal to this formula. Magnitude of the concentrated force times cube of the length divided by 192 EI. So if the beam is a simply supported beam with concentrated loads acting at every quarter points, so you can see here that the beam is divided into 4 parts, meaning the concentrated loads are applied at every quarter points. So the deflection that will be experienced by the beam, for this case, that will act actually at the midspan again, or center of the beam, is equal to this formula, 19 PL cube over 384 EI. P is the magnitude of the concentrated load applied. And then if the beam just supports two concentrated loads acting at every third points. So you can see here that the beam is divided into 3 parts. That's why we call the location of the concentrated loads as every third points. The deflection that will actually again occur at midspan or center of the beam will be equal to this formula. 23 PL cube over 648 EI. P is the magnitude of the concentrated load acting here on the simply supported beam. And then additional formulas will be this. So this is actually the general form of this formula that you have seen here. So the deflection at midspan at the center for a fully restrained beam acted upon by a single concentrated load P at a distance A from the left support and at a distance B from the right support is just equal to this formula. So the deflection at midspan for a fully restrained beam acted upon by a single concentrated load P is just equal to this formula. Product of the magnitude of the concentrated load and the distance from the right end, B squared, divided by 48 EI times 3 times the length. The length is the total length of the fully restrained beam minus 4 times the distance on the with respect to the right end or the right support. So for the case of fully restrained beam with concentrated loads acting at every quarter points, the deflection acting at the midspan or center of the beam will be equal to this PL cube over 96 EI. And lastly, for a case of a fully restrained beam acted upon by concentrated loads at every third points, the deflection at midspan or center will be equal to this 5 PL cube over 684 EI. So again, all of the deflections that we have shown here are deflections acting at the midspan or center of the beam itself. So you can use those formulas for finding the deflection acting at midspan for these particular cases of uh, beams with this particular load conditions. So again, this particular formula that you are seeing here can actually be used to derive this formula that you are seeing here. So you can just change the magnitude of A and B to be equal to L over 2. So just change the magnitude of B here to equal to L over 2 and then substitute it here on this formula. The result will obviously be equal to this formula that you are seeing here. And actually you can also derive the other formula, like for example this, with just using this formula here. You can just apply the concept of integral calculus. So later on, or maybe next time, I will show how to derive the the deflection at midspan for any loading condition for a fully restrained beam. Any loading condition, meaning whether it is triangular load or uniform distributed load or trapezoidal load, you can just easily compute for the deflection at midspan with just using this formula. So later on or next time, I will show you how to do that.